Often from logic alone, we can propose a reasonable distribution just based on the random process that we're trying to study. So if we wanted to study, say, people's checking account balances at a bank, well, we know those values are going to be strictly positive. It's probably going to have a right-handed skew because a lot of values will be concentrated maybe at the lower end of the spectrum, less than $100, but there'll be a few people with a lot in checking. And so the log normal distribution might be our go-to. And we might say, okay, let's propose to use the log normal distribution to model this and see what the consequences are. Now, as soon as we start collecting data, though, we want to make sure that our proposed distribution actually is reasonable. Now, we know that the real world is more complex than any probability model that we propose. We know going into this that all models are wrong. Our hope is that our model is going to serve as a reasonable enough reflection of reality to be useful and to answer some questions that we have. So once we've collected data, how can we check to see if our proposed probability model is reasonable? So we're going to take the same approach as we did in the discrete world and check to see if our probability model is reasonable through a graphical approach. So back in discrete world, what we did is we compared the empirical cumulative distribution function with the CDF, capital F, that was given to us by the proposed probability distribution. So what we could say is, all right, in my data, I see the number 3 a whole bunch. In fact, the fraction of data values that are equal to 3 or something smaller is 40%. So I want to compare that to what capital F of my probability distribution says it should be. If I see 40% of values 3 or less in my data, then the CDF evaluated at 3 should be pretty darn close to 40%. And we should have a pretty good match for x equal to 1, 2, 3, 4, all the way across the range. So we looked at that eCDF versus the formula for capital F with that stair-step plot, and we wanted to make sure that the points that we were observing, the empirical frequencies of the number of data values that are less than or equal to a particular value, is matching up pretty closely with what the proposed distribution is. Those points were falling at the outer corners of those stair steps. And so what I'd like to do for the continuous case is to do something relatively similar, but instead of looking at values from the CDF itself, let's go ahead and compare quantiles based on the data that we've collected and the quantiles that the proposed distribution says we should have observed. And so our main graphical tool for checking to see if a proposed continuous probability model is reasonable is the QQ plot, where we go and look at the quantiles in the data and see how well those match up with the theoretical quantiles that the proposed distribution can offer to us. So how does this work? Well, let's imagine that we've collected 100 data values. So in that case, we know what the value is in the data of the first percentile, the quantile 0.01. Well, that's going to be the smallest data value because 1% of the data values that I've collected are equal to that or something smaller. If I wanted to know, well, what is the 0.05 quantile? Well, if I've collected 100 data points, that's going to be the fifth smallest data point. Because by definition, 5% of the data values that I've collected will be equal to that fifth smallest value in something smaller. So it's fairly easy to measure the empirical quantiles, the quantiles that I observe in the data, the value of x that corresponds to the first, second, third, fourth, fifth, etc. Percentiles. And it's relatively easy for me to come up with what those values should be based on the proposed probability model. So all I have to do is solve for that inverse CDF, and I say, okay, for the fifth percentile in my data, I observed a value of 4.2. If I plug in 0.05 into my inverse CDF, my quantile formula, I can see, well, how closely does that value match up with what I saw in the data? And if the probability model provides a reasonable fit, well, I should have a pretty good correspondence between those empirical quantiles and the theoretical quantiles. So that's what we're going to do. After we've collected some data, we might be able to propose a reasonable probability model, but we're going to go through all the ones that we can possibly fit and just see, well, what happens to work in this case. And we'll do so by comparing the actual data values that we've collected with what those data values should have been based on the proposed probability model via this quantile matching. So the way that we're going to do this in R is to fire up the fitdist package once again and to use the fitdist function. It's going to work just the same as it did in discrete land. What we have to do is identify the abbreviation that R knows our notorious distribution by. And when we fit our data vector, we'll have that as our second argument in quotes, that abbreviation. And then once it's fit, we'll go and make a plot and see how that QQ plot comes out. How well are the observed data values matching up to what they should have been if that proposed probability model was correct? So let's dive right in and actually work through an example in this case. So every 10 years, the US government mandates that the census occurs. Basically, information from every household in the United States has to be collected, and the demographics of the United States are studied. So from a data collection point of view, it poses an interesting problem because not everyone is actually going to send back their census form. And by law, we actually have to get data on every single household. So the government has to hire workers to go and visit those households that didn't respond to actually manually collect the information. And so if we think about it, if we split up the United States, let's say, into various districts, it might be the case that the response rate varies from one district to another. In fact, if we fire up the reg class library, load up the ex2.census dataset, make a histogram of the values in the response rate, we actually see that there is a quite wide variety of response rates as we go from what's known as a housing tract to another housing tract. So there's a pretty big variety in response rates. Maybe we could come up with a probability model to model this distribution, which would aid in the planning of assigning these additional workers to go collect data. So looking at the shape of this distribution, well, what do we notice? Number one, it is always going to be positive. Of course, percentages are always going to be positive. It looks like it has a slight left skew because it takes its time to fall off towards smaller values. The fall off is relatively quickly to the right of the peak towards larger values. And by definition, these percentages are going to be constrained to live within 0 and 1, or 0 and 100%. So that indicates to us that potentially two distributions might work here. First, the Gumbel distribution. It's the only notorious distribution that allows for a left skew, except for the beta distribution. But the beta distribution requires us to have values of x that live inside of a set range. But we have that here. It's between 0 and 100. We can divide each value by 100 to get the number between 0 and 1, the natural domain of the beta distribution. So let's see how fitdist can evaluate the fits to this data to the Gumbel distribution and to the beta distribution. So let's just head on over to R and load up this data set. So this data set lives in the reg class library, and we want to load up ex2.census. So once that's loaded up, just for convenience, I'm going to extract out the response rate column. I'm going to divide that by 100, so the numbers go between 0 and 1, the natural domain of the beta. And this was the histogram that we had just looked at here. So left-hand skew, maybe Gumbel, maybe beta. Let's try it out. So just like we did for discrete world, we're going to left arrow into some object that we get to name. I'm just going to call it fit, the result of running fitdist. So first argument always is just the data vector, x in this case. The second argument is going to be the abbreviation of that distribution that you want to be fitting it to. The abbreviation for Gumbel is just Gumbel. And then we run it. And we say, all right, we've got that fit. We're going to run qqcomp on fit. That's going to produce the quantile plot, and this is going to allow us to evaluate how reasonable of a probability model this is. And this is a pretty amazing fit, to be honest. So on the vertical axis right here, we have the empirical quantiles. So these are the actual values as which we've observed in the data. And on the horizontal axis, those are what those values should be if the probability distribution was correct. So essentially what the probability model says is that, okay, when you're supposed to be observing values of around 0.7, what values do we actually see in the data? Well, right at about 0.7, maybe just a little smidge below. But overall, what we're seeing is that the values that we see in the data are matching up very closely with what they should have been if the Weibel distribution was correct. There's a little bit of peeling off at the top right and at the bottom left here. That almost always happens. The tails of a distribution, kind of the extreme values, are always very difficult to fit. But what we see is that overall, that's a pretty darn close fit. Maybe a little bit of a dip beneath that line, maybe at around a theoretical quantile point, about 0.62, but overall pretty good. And so this is what we would like to see. We would like to see a perfect correspondence between the data values we've collected and what they should have been if the probability model was correct. We're always going to see a little bit of wiggling, and so there's a bit of a leeway. What we want to make sure is that we don't have some very obvious systematic curvature away from that straight line, some sort of deviation between what the values should have been and what we actually observed. So, for instance, if I were to go and fit this to a normal distribution, just changing the abbreviation, I don't want to see this. This is not great because we have this systematic bend away from that diagonal line, indicating that there's a systematic departure between what a normal distribution can give us, the shape of that, and the values that we're seeing in the data, the shape of that histogram. And that wasn't really too much of a big surprise because we had seen that the histogram had a bit of a left skew. That normal distribution is quite symmetric. So it looked like the Weibel provided a pretty decent fit. Well, the other one that we had in mind was the beta distribution. And so let's try that out. Once we try that out, well, it's a reasonable fit. It's a pretty close correspondence between the data values that we're observing and what they should have been if the beta was correct. Pretty close correspondence with the diagonal line. But there's a bit more of a peeling away at this lower value. So there's some systematic departure between the values that we've collected on the lower end of things and what those values really should have been if the beta distribution was correct. So there's some systematic problem with this distribution. We would say that the beta distribution, overall a reasonable fit, but not the best. I would definitely go with the Weibel in this case. It looks like that provides the better fit. What are some other ways of assessing the fit besides just the QQ plot? Well, you can look at other plots if you would really like to. I think the QQ plot is really the main one. But of course, one thing you can do is look back at the histogram and see, well, how well does the shape of the distribution that's been proposed actually match that shape? So there's a few ways of doing that. We can make a histogram actually, making sure to have freq equals false so that they're not counts, they're just relative frequencies. And then we can pass an argument called breaks that says, okay, here's where I want those bars to start and end. So here's our response rate data visualized. We're going up from 0.3 up to 1 in increments of 1 percentage point here. And so these bars are actually pretty skinny. We see that left-handed skew. And we could say, all right, so what does that Weibel distribution actually look like? If we fit that Weibel distribution, what we can do is we can get a summary of that fit to see, well, what parameters did it actually extract out? The Weibel has two parameters, a shape parameter and a scale parameter. And so if I want to use that Weibel and a curve of that Weibel to see how close of a fit I have, well, what I can do is I can run the curve function, just put in the D version of the PDF that I want to be looking at, D Weibel in this case. X is the argument for curve that it always wants. And for the second and third arguments, basically for the D Weibel function, what's the value of the shape and the scale parameters? Well, we can copy and paste that if we want, or we can always just use fit $estimate bracket 1 for whatever the first parameter estimated, and then fit $estimate 2 for that second parameter. We're going to add equal true that so we don't create a new plot, and we're going to make this red. So we can add that curve. Maybe we want to add some thickness to that curve. And we see that it really is a fantastic fit. With that beta distribution, well, if I rerun the fit to the beta and change this to d beta, let's actually add this. We can continue to add more and more curves. I change the color to blue. we can see that, there's just a little bit of a difference between what that beta distribution is giving us and what the Weibel distribution is giving us. If you remember, the beta distribution wasn't doing the best job at modeling some of those lower values. Kind of hard to tell, actually, from the histogram with the superimposed PDF. That's why we like the QQ plot a little bit better. All right, well, last plot that we can look at actually is harkening back to discrete world, where we compared the empirical cumulative distribution function and the CDF that is proposed by your probability model. So I'm going to go back and refit this to the Weibel distribution, and what we can do is we can run the function CDFcomp. And so this will show us that empirical cumulative distribution function, basically the fraction of data values that are less than or equal to a certain value. So the fraction of data values that are less than or equal to 0.8, tracing that curve up, looking back about 58, 60% or so. And then in red, really skinny red line, we can see that those CDFs match really quite fantastically. And actually, there's one more function in fitdist you might want to know about. Instead of manually making that histogram, what you can actually run is the densecomp command. That'll make the histogram as well and superimpose that PDF, but it doesn't give you as much control over what those bars look like, so I kind of just like making it by myself. All right, so what happens when we want to fit a distribution that's not part of our notorious zoo? Well, fitdist allows us to do that. We just have to define a trio of functions for that to happen. So in order to fit our own custom distributions, number one, we have to come up with an abbreviation that we want to use to call our distribution. You can just call it custom, you can call it mydist, whatever you'd like to. Cannon, Jackson, knock yourself out. But once you've identified your abbreviation, you need to define 3 functions that use that abbreviation. Put a D in front of it, you have to define the D version of that function. The formula for the PDF, you have to define the P version of that function as well, pcustom, the formula that gives you the CDF, capital F. And then you also have to define the Q version of that function, the quantile function, qqcomp. So we didn't have to do that back in discrete world. We had to do the first 2, so we've talked about that before. For a continuous fit, we actually do need that Q version of that function as well. And so let's try this out. Let's imagine that I have a PDF in mind that I want to fit to my data. And the formula for my PDF is just x minus 19 over 128. So x lives inside of a range between 19 and 35, and I want to see how well this PDF fits my data. So I need 3 functions, basically dcustom, which is just transcribing the formula for my PDF. I can write that out pretty quickly. Then I need to figure out, well, what's the formula for the CDF, capital F? And so I can throw this into Wolfram Alpha, ask it to integrate the formula for my PDF from minus infinity up to x, but not really minus infinity because the lowest value that's possible is 19, so 19 is the lower limit. And I would find my formula for the CDF is fairly easy to work with. And then once I have my formula for the CDF, I can take that formula, set it equal to q, and solve for x to figure out what my quantile function is going to be. So once I know what my PDF, CDF, and then the quantile function are, all I need to do is define what those functions look like in R, write my dcustom, pcustom, qqcomp functions, and then we can run fitdist. In order to make this go as smoothly as possible, and just to make it look like all the other fits that we do, what I'm going to do when I define dcustom, pcustom, and qqcomp is to actually add kind of a fake second argument. So in this case, this PDF doesn't have a parameter that we can tweak to change its shape. It's just one shape. So others like the normal, it has 2 parameters, the beta 2 parameters, the Weibel 2 parameters, exponential 1 parameter here. Let's pretend like we have a parameter that controls its shape. This just makes the fitting a little bit easier. The formula is going to stay the same. I'm not going to change that. I'm just going to add in a second argument to make things smoother. Oh, and I guess one last note, fitdist is very particular on the syntax. When you define dcustom, that first argument has to be x, and you have to write your formula in terms of x. Pcustom has to have as its first argument q, and then you have to write your formula with the letter q. And qqcustom has to have as its first argument the letter P. And then you have to write your inverse CDF using the letter P in the formula. So let's define dcustom, pcustom, qcustom, and let's generate some data values just so that we have something to play around with. So the nice thing is that the qqcustom function actually provides you a way to go from uniform numbers between 0 and 1 to actual values from this distribution using that inverse CDF transform. Just generate the quantiles of the data values at random and then figure out, okay, well, what value of x does that quantile correspond to? So my inverse CDF transform gets me a bunch of x data values. That's what they look like. And so what I can do is the same thing as I did in my previous examples, where I just say fitdist and custom. So why custom? Well, that was the abbreviation that I came up with. You're free to choose whatever you'd like to have. It can be Jackson Cannon, it can be mydist, whatever you want to do. The key thing is that D, Q, and P have to precede that abbreviation, and then you'll put that abbreviation in quotes when you run fitdist. So if we run that, we get a little error because when we have a custom distribution, R says, okay, give me a little bit of a hint about what that parameter might be. So we have to actually say list A equals 0 here. It just needs a little, this is just to get it to work. We don't actually ever use the value of A anywhere, but fitdist is not smart enough to figure that out. So we just have to say start equals list and then give it some starting values for what those parameters might be. It'll figure out the best values when necessary. In this case, there's nothing to estimate, but we did it. So now we can plot our fit. We get the whole array of diagnostic plots, or we can run qqcomp. And it looks like we got a great fit. But of course we do because the data, we generate it through the inverse CDF transform from this PDF, so it should have been good. All right, another example, and this one actually utilizes the parameters of the distribution, is a PDF known as the Gumbel distribution. And the Gumbel distribution is one of these extreme value type distributions, which are really useful for measuring the maximum value of a random sample. So if everyone, for whatever reason, had measured the fastest that they've ever run, and we look to see, well, what's my value for the fastest? What's your value for the fastest? What's Ted's value for the fastest? It turns out that the PDF that does a good job for describing maximum values in random sample is very often a Gumbel distribution. So kind of a cool application. So in this case, what I'd like to do is to try to fit a set of data values that I'll generate to a Gumbel distribution. This isn't in the notorious zoo, so I need to define my 3 functions. So the abbreviation that I'm going to use is just Gumbel, and I'm going to define the D version, the P version, and the Q version of those functions. So all I have to do is to transcribe these formulas. After a little bit of math or looking it up on Wikipedia, I can see what those formulas are. The key thing is, once again, the D function has to have as its first argument x. I write my formula in terms of x. The P function has to have first argument q. I write my formula in terms of the letter q. And the Q function needs to have as its first argument p, and I write my equation in terms of the letter p. So in this case, there's 2 parameters, A and B, that control the shape of this distribution. And so my second and third arguments are going to be those 2 parameters. So let's get that into the global environment. And now let's generate some data to fit. So once again, this is actually one of those distributions where I could use that inverse CDF transform. I can generate the quantiles at random between 0 and 1, and then look back and convert those into the values of x that they represent. And so that's where my data vector x is coming from in this case. All right, now when it's time to run fitdist, first argument is my data vector. Second argument is the abbreviation that I've come up with, just Gumbel in quotes. And then because this is a custom function, I'm going to have a third argument that is start equals list. And then in that list, parentheses, I'm going to put A equals 25 and B equal to 3.5. Just some starting guesses for what those 2 parameters are that are controlling the shape of the distribution. Fitdist will go and figure out better values. It just needs a little bit of a nudge to get started. So once we fit it and then we run the qqcomp, we see a great fit because of course we do. this is the distribution that is generating our data values, and so that's a great fit. All right, back when we were trying to fit a distribution to the response rates for the census, we considered the Weibel distribution and the beta distribution, because they both were able to give a left-handed skew, and in this case the values ranged between 0 and 1, so the beta distribution was always going to be something we wanted to investigate. And from the shape of the QQ plot itself, it wasn't excruciatingly obvious which was the better choice. They both look to have pretty reasonable fits to the data. So how in general should we be deciding which is the best probability model? So some really smart people back in the day sat down and thought really hard about, well, what criteria should we be using in order to figure out the best probability model? And so let's go through one line of thought. So as an example, let's imagine that the reality is that the true distribution that's generating our data is given to us by this black curve. And there are two distributions that I'm proposing, and I'd like to know, well, which one is the better probability distribution? Is it the distribution given to us by the blue curve, or is it the distribution given to us by the red curve? Now, just looking at it, we can see that the blue curve is a lot closer to the black curve than the red curve is. So we can immediately tell that, okay, the best probability model is going to be the one given us to by the blue curve. The question is, how can we actually write down something mathematical or some sort of number that kind of reaches the same conclusion as what we're doing with our eyeballs? In general, we don't actually know what the true distribution is that's generating our data, that black curve. So given the blue curve, the red curve, and some data, how can we really tell, which is the better distribution to use? So the way that we're going to measure how close two distributions are is to borrow a page out from information theory. Specifically, we're going to be computing the Kullback-Leibler divergence between two probability distributions. So if we have some probability distribution in mind, f of x, maybe that's the true distribution that's generating our data, we'd like to know how far off is our proposed probability distribution g of x. So what we can do is calculate this relatively complicated looking integral, the log of the ratio of the heights of the two PDFs times our formula for f of x integrated over the range of possible x's that we might see. So what is this formula actually trying to convey? What is it really measuring? Well, it's measuring something like the percentages different that the heights are for the f and g curves as we scroll across the possible values of x. It's a little bit more sophisticated than that, but if you want to convert it into just kind of a graphical measure, we can kind of treat it, and this is a vast oversimplification, as something like the area between those two curves. Now, once again, vast oversimplification. That formula doesn't really equal the area between those two curves, but we can kind of think of it as if it does. I think that kind of gets to what the heart of the meaning of that Kullback-Leibler divergence is. And so in this case, we can see that there's very little area between the blue and the black curve. It's pretty close. They're pretty close together. But there's a lot of area between the red curve and the black curve. So there's a pretty big distance between those two probability distributions. So the specific formula actually emerges from information theory. It's an entropic measure, kind of a crazy cool concept. But the key thing is that provides us a number that serves as a yardstick for us to measure how far apart two probability distributions are. So we have the true distribution that's generating our data f of x. How far away is g of x from there? The closer, the better. So why don't we go and actually measure the Kullback-Leibler divergences for a whole bunch of different probability models that we propose and see which one has the smallest value. Well, that sounds like a great plan, but there's a big problem with that. We don't know what the truth is. We don't know what probability distribution is actually responsible for generating our data, so this formula is kind of useless. We can't actually go and compute the value because we don't know what f of x is. And that's our whole goal of fitting the data to distributions. We want to know what distribution is making our data. So how can we measure how far off a proposed distribution is from the truth without knowing what that truth is? Well, back in the 70s, a very brilliant man by the name of AICs came up with a way to estimate this difference from just a data set and a proposed distribution. So he figured out that a way to estimate what the value is for that Kullback-Leibler divergence was to take the likelihood of the data, essentially what is the probability of observing your data given the proposed probability model, and then account for the complexity of that probability model by accounting for the number of variables, parameters, that we can tweak to give it different shapes. The more parameters, the more flexibility, the likelier that we are to be able to come up with something that fits the data pretty well. And so he figured out that one good way to estimate that Kullback-Leibler divergence is to take the log of the likelihood minus the number of parameters of that distribution. So in some ways, kind of balancing how well that probability model fits the data via the log likelihood, the probability of observing your data with that particular probability model, and the complexity of that model via the number of parameters you're allowed to tweak. And so you might have seen this, this term before, the AIC, or AICs information criteria, minus 2 times the log of the likelihood of the data plus 2 times k. We'll talk more about likelihoods coming up. You'll learn to love them, I hope. Provides us a decent way to measure how far off a proposed distribution is from the true distribution generating that data without actually knowing the truth. So lower values are better. The closer to the truth we are, the better that proposed probability model. And that's going to be our strategy. If there is any doubt lingering in our mind after we've run qqcomp and actually look to see how well those distributions are fitting the data, we can get the AICs of the fits and then just go with the model with the lowest AIC. Now, is there some sort of threshold that we have to beat in order to have a convincing reason to go with one probability model versus another? Well, yes. I like using the guideline that in order to be a convincing front runner for the best probability model, that probability model has to have an AIC that is at least 4 below the AIC of the runner-up. So I usually like to say that differences in AIC of less than 4 don't really provide us with compelling evidence that one probability model is better than the other. But if it is bigger than 4, well, that's pretty good evidence that the model with the lower AIC is going to be the better choice. So let's go through an example where we really do need to use the AIC to help us make up our mind as to which probability distribution is the most appropriate. So I'm going to load up the reg class library and then load up the PIMA dataset, which has information on women in the PIMA tribe in the United States. Now, the information that we have is the number of times she's been pregnant, her glucose level, etc., etc. Originally, this dataset was used to help make predictions as to what factors were most associated with having diabetes or not. But what I want to look at is the distribution of body fat percentages. So let's take out the body fat percentages, which right now go between 0 and 100, divide by 100 so that they go between 0 and 1, the beta distribution's natural domain. And here's what we see. So roughly symmetric. Maybe the normal distribution works okay. Maybe the beta is pretty good. Maybe some other alternative is going to be the best choice. So let's go through the distributions in the notorious zoo and see which one is going to be the most appropriate here. So let's start out with that normal distribution. So if I go ahead and run fitdist on the normal distribution, the qqcomp shows that it provides a pretty reasonable fit. Sure, there's a little bit of peeling away at the left edge and the right edge, but we see that even when the probability model is fairly good, so not a deal breaker, for the most part, the observed values in the dataset are matching up with what they should be if the probability model was correct. And so we can ask, okay, well, what's the AIC of the fit? We get a value of minus 650, and here's an important thing to note about the AIC is that the actual value itself is pretty irrelevant. It can be negative, it can be positive. It's not the actual distance between the proposed probability model and the true probability model making the data. It's really just a relative measure, where the smaller that the AIC is in respect to comparing with other values of AIC, the better off we are. So before moving on to the next distribution, we should ask ourselves, can we really even use the normal distribution here? Because the normal allows negative, positive values. Body fat percentages are always positive. So we just need to make sure that the normal model isn't allowing too much of a probability of allowing a negative number. We can manually calculate, well, what is the probability with this model of getting a negative number? Scrolling up, we find that the average is right around 0.3, the SD is about 0.1, and so if we just ask for p-norm of 0, the probability of getting 0 or less, with a normal distribution with a mean of 0.291 and a standard deviation of 0.105, we see that probability is very tiny. So negligible. The normal model would be okay to model this data set. Okay, so the normal AIC minus 650, let's see if we can do better. Let's fit to a log normal distribution. That has to be a positive number, so that's great. Running qqcomp, not good. We see that big peeling away off towards larger values. We see a big hump kind of in the middle, all above the diagonal line. Not a great fit. So the AIC reflects that. Much, much bigger than the AIC of the normal. So bigger than 4, definitely evidence the normal is a better distribution. Let's leave the log normal behind. All right, well, what about the Weibel? We can fit it to a Weibel. We can look at its QQ plot, and that looks pretty darn good. The values we see in the data are matching up really closely with what the probability model suggests they should be. What about the AIC? Minus 650 is what we want to beat. Minus 661 is way below that. More than 4 below that, so we now have a clear preference for the Weibel. All right, well, the gamma distribution is something we can test out. We mentioned it for about 5 seconds in the notorious zoo. It doesn't really play a huge role in analytics, but you never know. Its qqcomp is disappointing. So we got a bulge in the middle above the line. We got that peeling away from the line at higher values, and the AIC is going to reflect that. Quite a lot larger than the minus 661, comparable actually to the fit of the normal, but definitely Weibel is our favorite. All right, beta distribution, we scaled these numbers to be between 0 and 1. The QQ plot reveals that it looks like it's a pretty darn good fit. What's the AIC? Minus 661.5. So here we ran into actually quite a few fits that looked reasonable based on the QQ comp. The AIC definitely helped to serve as a tiebreaker. We're seeing that the Weibel and the beta definitely would be the models that we would prefer. Can't really distinguish between the two, don't have a clear preference there because their AICs are within 4, but it definitely let us know which ones seem to be the closest to whatever probability distribution is responsible for making our data. All right, one little twist with using qqcomp that you want to be aware of is when you're dealing with very skewed distributions. So one example is in the account dataset in the reg class library. If you look at a histogram of the amounts that people have in their checking balances, you see that the vast majority of people have checking account balances that are relatively small. There's a few outliers, so it's kind of hard to tell what the shape of the distribution is at all from the histogram because most of the values are in that very first bar. So if we restrict ourselves just to people that have, at least $1 in their checking account, we fit this to a log normal distribution. Kind of, well, why not? If we look at a qqcomp, it's kind of difficult to tell, well, is that a good fit or a bad fit? It looks like a bad fit because we see a whole bunch of peeling away from that diagonal line at larger values. But since the vast majority of values were much, much closer to 0 than what the qqcomp plot is allowing us to see, we should really remake this plot to add a bit of clarity. So when we have a really skewed distribution, I always suggest adding in an additional argument to qqcomp that allows for logarithmic display of the axes. So x log scale equals true, and also y log scale equal to true. That'll make the QQ plot on a log scale, and that'll allow you to glimpse kind of what the fit really looks like over the full range of data values that have been collected. So that strong peeling away that we saw at larger values in the previous plot doesn't look so severe anymore, but we do see a pretty big issue with values on the lower side. This model seems to be doing a pretty poor job of reproducing the frequencies of people having values between about $1 and $100 in their checking account. So what do we do if there isn't going to be a notorious model that's going to help us out? Like if our distribution is bimodal, or if we just have a shape we've never seen before? Well, one recourse, one kind of modern development in probability theory is to abandon the whole framework of trying to come up with a formula for the probability density function and instead rely on the data itself to propose a reasonable curve for what the PDF might look like. So we can use what's known as a kernel density estimator to actually come up with a smooth curve that gives a good idea of what that PDF is just from the observed data values that we've collected. Now, a classic example of this is the Old Faithful dataset. So looking at a histogram of the eruption times of Old Faithful, we see it's clearly bimodal. peak near 2, peak near about 4.5. There's nothing in the notorious zoo that has bimodality, so we're kind of stuck unless we get creative. So here's what we can do. The kernel density estimator says, all right, why don't we go ahead and represent each data point that we've collected as a little itty bitty normal curve. And then what we'll do is we'll stack up the normal curves from each different data point until we kind of get an overall shape of that distribution. So in this plot right here, we have 3 different observations, the black, the red, and the blue observation here. If we just represent the black point by a small normal curve, the red point by a small normal curve as well, and then just add up the heights of all those curves, well, we kind of get a nice smooth approximation for maybe what the curve of the PDF that's generating that data. And so we kind of go with that. The kernel density estimator says, all right, well, let's just approximate the shape of that PDF by just summing up a whole bunch of the heights of normal distributions. So the density, or the formula for that curve, density x here, is really just the sum of a whole bunch of normal distributions. They're centered at each individual data point that's been collected, x1, x2, etc. And the width of that normal curve, the standard deviation, if you will, is what's referred to as the bandwidth of that kernel density estimator. The larger the bandwidth, the kind of more spread out that normal curve is, the smoother the resulting curve's appearance is really going to be. So we get to tweak the value of the bandwidth. It can be small, it can be large. We kind of choose a value that looks reasonable to us, and we can use that actually as a good stand-in for our continuous probability model. So tweaking that bandwidth parameter with the Old Faithful data, if we have a really small value of the bandwidth, we're going to get a lot of wiggliness. Those normal curves placed at the values of each of the data points are really, really skinny, so we get a lot of up and down, up and down. A little bit artificial. Probably don't think the real distribution looks like that. On the other hand, if the bandwidth is too big, the curve gets to be a little bit too smooth, and we lose some of the structure that we easily see in the data. There's going to be a happy medium. Normally R chooses a smart value for what the bandwidth is, but we can tweak this up and down. Now, once we kind of have a shape that we like, a bandwidth that we like, how can we really use this? Well, here's an example. Here I've extracted out the eruption time data from the Old Faithful into the vector x, and what I've done is I've plotted the kernel density estimate with a bandwidth of 0.3. And I like this shape. Let's say I want to go with this. Maybe I want to generate random numbers from this shape. Well, if I want to use this, say in a Monte Carlo simulation, to generate random numbers from, what I can do is I can set it up to just have a valid range of x that I'm allowed to actually pick from. Now, instead of a continuum of values, I'm actually going to go up in small discrete increments, in this case, increments of 0.01. I'm going to give the smallest value that I'm interested in generating, 0 in this case. 7, I'm going to have as the largest allowed value that I'm interested in generating. And so I'm going to look to see what the height of the PDF is all along from 0 to 7 in increments of 0.01. And then when I run the density command, I'll pass that bandwidth that I like, and then I'll tell it to actually evaluate what the height of that curve is along that sequence of x values that I've set up. And so I'll define a possible.x to be the values that I would see if I were going to use this for a Monte Carlo simulation. So pick one of those values at random. The height of the curve would just be the $y parameter of that density object. So if I go and say, well, let's make a bar plot. And so once I set that up, I can use the bar plot command to really visualize what I've created, or just the plot command here. Here I'm having the heights of the bars just be the PDF, the y values that I extracted out from density. The names are just the possible x values. And so I've been going up in such small increments that it looks like a smooth curve. I could also just plot PDF twiddle possible x, and that would just put points for each one of those possible values of x and the heights of those curves. So I see I'm doing a good job reproducing that shape. They're within 4 of each other, so there's no compelling reason to go for one distribution or the other. Beta, Weibel, take your pick. Your favorite ones.